Hello, this is Dr. Hasan Abdullah with the course Deep Reinforcement Learning, and the topic is Dynamic Programming, which is the 11th topic in the list of topics covered in this course. And the subtopic is B, so this lecture is 11B. So basically, this lecture has a difficulty level of easy to moderate. And this video lecture is developed using the supplemental website www.easymcq.com/GoGet, which is a personalized learning management system. So, what is the future of content delivery? That is not the future alone, that is also the present, because there are literally hundreds and millions of end users who are getting educated using the content delivery platform and mechanism, which are in hundreds and millions. So, that is the approach which is being used in delivering and explaining the concepts in this course. So, the personalized learning management system is accessible using the URL which is given in green color, and the content delivery mechanism is explained using 6 videos, and those videos are accessible using the link given in blue color. So, what are those features which I've mentioned? These features consist of advanced and basic content search, which is not there in leading learning management systems. And then, of course, the ability to support people with visual disability, such as changing the font size, color, line spacing, and so on. And then this content is organized in such a way that it can efficiently use the limited speed, the limited space and the speed of a handheld device. And of course, you can track your progress, what you have seen, done, and what you need to do. And then, of course, you also can test yourself online in real time, your knowledge assimilation and knowledge capturing. So, how the content is delivered? The content delivery can be question and answer based, and it can be traditional slides based. Now, the question and answer based approach is engaging, is proactive, it promotes thinking, and of course, it is very productive also. And the traditional approach contains a lot of details. So, the approach we have been following in this course is a blended approach, which is the best of both. So, this is the list of topics which are covered in this course, and we are at topic number 11, which is dynamic programming. And this is further divided into certain number of concepts in the form of questions and answers. So this lecture 11A consists of the concepts in yellow background color, and the next set of question and answers are in green color, that is 11B. Now we move on to the details of the lecture. So we are at lecture 11B, deep reinforcement learning. The topic is dynamic programming. So the question is, how is dynamic programming used in reinforcement learning algorithms? So that is not a traditional approach or traditional way of using dynamic programming, but still dynamic programming plays a crucial theoretical and algorithmic role in reinforcement learning. As I said, it is not commonly used directly in large scale and real time applications due to certain reasons, such as its reliance on complete environment models, which may not be there in case of real life, and the computational demands. But still, it forms a, so it's a backbone of reinforcement learning methods. Now, in the scenario of deterministic Markovian decision processes, now Markovian decision processes we have not covered because that's not part of this course. But we did cover Markovian hidden Markovian systems. So deterministic means that they basically there's no randomness. So the answer is going to be repeating for the same input. Now they offer precise and efficient solutions. How? Through the mechanisms like policy improvement, which is part of reinforcement learning. So dynamic programming iteratively refines the actions. So iteratively the actions are refined, and how it is done, it is based on the estimations of values. That leads to near optimal policies. And maybe most significantly, dynamic programming enables robust evaluation of policies through accurate value computations. So we are looking at solving the deterministic Markovian decision processes, and we are interested in policy improvement. And this robust evaluation is achieved by using the Bellman equations. Now, I'll explain what this figure shows. So, these concepts are directly reflected in many modern reinforcement learning algorithms. However, there's no point in giving their names. So, but one thing is common, the environments where models are known or can be estimated. The models which we discussed in reinforcement learning. So, in such scenarios, dynamic programming remains a gold standard, a kind of a reference for evaluating the quality of the policy. Okay, so details are here. We will cover those details. So, understanding dynamic programming has a benefit. It allows reinforcement learning practitioners to help build more effective and theoretically better algorithms, which of course is an essential part of the overall reinforcement learning optimization. I will go through these details. So in this diagram here, and as you saw earlier also, so we have a grid, and in this grid there are arrows. So what do these arrows do? That they point towards the terminal states 0 0. So this is a grid, 0 0 terminal state, this is 3 3 terminal state. And the policy, as we discussed in reinforcement learning, just a reminder that the policy or rules are the decisions which the agent takes when in a certain state to go to another state. Okay, so these arrows guide the agent to reach the terminal states. So this is one terminal state at 0 0, and this is another terminal state at 3 3. So now solving the deterministic MDPs. So solving the deterministic MDPs, Markovian decision processes. So dynamic programming is very effective, but for deterministic MDPs, and because where the transitions are predictable, unlike stochastic ones. So there is no randomness. Therefore, value iteration can be applied directly to find optimal policies. So these models are often used in simulation, robotics, or testing environments. Why? Because their exact outcomes of actions are known in advance. Well, this is not very practical, and it does not matches the real world stochastic environments which are non-deterministic. But still, deterministic dynamic programming models are important from educational point of view because they serve as a foundation for understanding more complex and decision making with uncertainty, which is real life. All right. So let's move to policy improvement. So policy improvement, as I said before, is an iterative process, and what it does, it refines decision making using the value functions that we covered briefly in reinforcement learning. Remember that there is a whole course on reinforcement learning. We have just touched upon a small topic. So so dynamic programming methods compute the value estimates for a current policy and then update the policy by choosing actions that result in higher expected returns. So there's a feedback loop here. And what that feedback loop does, which is there in reinforcement learning, that each iteration leads to a better or of same quality policy. So ultimately, it converges to an optimal one. So this principle uh, basically helps many hybrid uh, reinforcement learning methods, right? Which split learning into evaluation and improvement phases. I'm not going to a lot of details, but just to give you an idea. Robust evaluation. Now, with full knowledge of the MDP's dynamics, when I say MDPs, basically I'm talking of deterministic. So, dynamic programming offers highly accurate policy evaluation. How? Using the Bellman equation. So, basically, this evaluation forms the benchmark for reinforcement learning approaches, and it is very critical and it's important and it's instrumental in ensuring convergence and stability of learning. And when it's most useful, when for model based environments, model based scenarios. Therefore, this is like a gold standard. Although it may be less scalable for large state spaces, but still its exactness and convergence guarantees and make it a central, give it a centrality in reinforcement learning theory and corresponding algorithm design. Okay, so this I've explained to you. So, so let's look at how dynamic programming is used in speech recognition or part of speech tagging. So, what is meant by part of speech tagging? That is covered in the course Natural Language Processing, which of course is available. The full course is available on this web portal also, NLP. So, part of speech tagging means that, say, for example, I have a sentence, and what should be the association of a word grammatically in that sentence. For example, a book is used as a verb, booking a seat or a book is a noun, or ran is or run is, it can be an action, or it could be running, or it could be, so bark also. So we see that a dog is barking and the bark of a tree. So it depends upon the context in which the word is used. So how dynamic programming is applied in speech recognition? So it plays a pivotal role in speech recognition and part of speech tagging. How? By enabling efficient and accurate sequence decoding. And there are, how it is done. It is done using the Viterbi algorithm, okay, which we have briefly looked at, and hidden Markov model also, which we have also briefly looked. We have not covered all of this because that is not part of this course. This course is deep reinforcement learning, and further details or extensive details could be in a course on reinforcement learning. So what the Viterbi algorithm does is it applies dynamic programming principles to infer the most likely sequence of hidden states. Hidden states over here means that if the word book is used, then it a verb or a noun. So that's the hidden state. And then it avoids computationally expensive brute force enumeration, that this is how it can be used, this is how it can be used, and this is how it is used. So looking at all the permutations, so that is computationally prohibitive. Now, if we use the hidden Markov models, they provide a probabilistic framework. Okay, how the observations depend on unobserved underlying states. So this the word book is used as a verb or a noun, and the bark is used as a verb or a noun. Now these models rely on well-defined transition and emission probabilities, which we discussed, and dynamic programming can exploit for efficient inference. Now, efficient decoding ensures real-time applicability of these techniques. Real-time requires a lot of processing powers, and that requirement can be a limitation for large data sets or long sequences or noisy data. So that we will discuss. So in deep reinforcement learning, these ideas form the foundation, modeling in sequential decisions or partially observable systems, which is a reality. So let's look at more detail in at those bullets. I will explain this diagram. So the Viterbi algorithm. So Viterbi algorithm basically is dynamic programming, and it used to determine the most probable sequence of hidden states. Okay, which we don't see, but we can observe their impact. And it is widely used in speech and language tasks for efficient decoding. Now, by storing the optimal subproblem solutions, that's how dynamic programming works. It drastically reduces the computational complexity. So instead of use storing all the subproblems, only storing the optimal. right? Otherwise, it will be computationally prohibitive. So that makes real-time inference feasible, not pure dynamic programming. And it has a positive influence on deep reinforcement learning models, where inference is required over sequences. All right. So, with reference to the hidden Markov models, they provide a statistical framework for modeling sequences with hidden structures, such as part of speech tagging. Now, what these models do is that they combine the transition and emission probabilities and capture the sequential dependencies specifically between the words. And they are, of course, integral to traditional natural language processing and speech systems. Why? Because they inspire the belief based reasoning. So that's not a black box approach for deep reinforcement learning environments. And finally, is the efficient decoding. So, what is efficient decoding? Basically, this again leverages dynamic programming to process long observation sequence and without the exhaustive search, because then the state space becomes unmanageable. And then, of course, then this underlies real time applications like speech recognition and part of speech tagging and so on. So, in deep reinforcement learning, the same principles guide uh, the belief updates, the sequential policy learning, which is more of the domain of reinforcement learning, and memory based action selection in a complex temporal environment. Okay, so let's closely look at this processing of the statement here. So, so this is example of part of speech tagging. So Bob is a subject and is a noun, and this a book collector. So we have subject object. Okay, and this object is a compound noun which consists of a book collector. And you can see that over here the book is an adjective, collector is a noun. So similarly, we have verb modifiers. So made is an uh, adverb, like word modifiers the other day, that further divides into an adjective and a noun. So this is all which is done and more in part of speech tagging to make sense out of the sentence. Uh, Dynamic programming has played a central role in the early development of reinforcement learning. And foundational algorithms like several, like say, value iteration and policy iteration, which we have not covered, not part of this course, and they leveraged on the Bellman equation to solve the Markovian decision processes, which we touched upon. So these methods actually work exhaustively, like a brute force approach. Okay, and this is done, or they update value functions across all states and actions until convergence is achieved for an optimal policy. Now, dynamic programming is mathematically elegant and it is provably optimal for small, well defined environments. Like Dijkstra algorithm is also dynamic programming, but it falls short when applied to large scale and high dimensional problems, okay, like deep reinforcement learning. All right. And so, deep reinforcement learning deals with complex and continuous environments like robotics, games, autonomous driving. So the state and action spaces are vast and infinite. State space, this is what is called as the state space explosion. This is very large, okay? And in such settings, dynamic programming suffers with several critical limitations. What are those limitations? Those limitations are listed here. Now, taken together, these limitations highlight why dynamic programming is largely incompatible with deep reinforcement learning. So this space explosion and lack of generalization render dynamic programming infeasible for large or continuous domains. So it depends on a fully known model, which is not as per real life. Furthermore, because of this state space explosion, the computational demands of dynamic programming make it unsuitable for real time, scalable learning, which is required in deep reinforcement learning. Now, dynamic programming uh, remains foundational for classical reinforcement learning theory and the modern applications rely on approximate, model free methods. So, dynamic programming is more of a conceptual stepping stone because of these reasons. It is not the perfect solution. So, let's go over these aspects of dynamic programming briefly, one by one. All right. So, dynamic programming methods fail in environments with large continuous state spaces, which the figure I've just shown you, and it's here at the bottom of the screen also, because because they rely on exhaustive enumeration. Now, therefore, each state must be visited and stored explicitly, worked on it explicitly, and this becomes computationally prohibitive, and it is not feasible memory-wise. So, deep reinforcement learning addresses these issues through function approximation, which we have done in a lot of detail. So that allows, since we are working with approximation, so that allows generalization, not perfect generalization, generalization over vast or infinite spaces. Then is the model dependency. Dynamic programming requires a complete, accurate model of the environment. Now, this is not the case. This is actually that is rarely true in real world problems. Therefore, it becomes impractical for most deep reinforcement learning settings uh, to use dynamic programming. Why? Because we have unknown environments. Now, deep reinforcement learning kind of thrives in such cases by being model free or using learnable and approximate models. So, we are trying to approximate the loss function. Then is the computational complexity. Dynamic programs are iterative and they require a full sweep or coverage of the entire state action space. Therefore, this is computationally prohibitive, intensive, and is not scalable. So, dynamic programming lacks the efficiency of deep reinforcement learning techniques like mini batch updates or gradient based learning, which are basically optimized for large scale computation. And finally is the generalization failure. Dynamic programming treats each state independently. That's why it works. So that prevents any form of generalization. And in contrast, deep reinforcement learning capitalizes and leverages the neural networks for generalization across similar inputs. And that makes them vastly more scalable and data efficient and specifically for high dimensional environments. So, what we see here is that this state space explosion is one of the most prohibitive factors of using dynamic programming. So, the details are here, okay, so you can go through them, and here are the additional references. All right.